And welcome back to another lesson on transformations. This is the week of transformations. Hopefully we can get a nice solid foundation for this stuff by the end of the week. And today we're actually focused on actually graphing these transformations. So if you didn't write these notes down or you didn't screenshot it, I recommend taking a look at this slide right here and using this as a reference for when we do our work for being able to transform functions. Now, we're going to go over 3 examples today. This is the only video for today, so once you're done with this, make sure you do those problems. So here's example 1. Here's f of x. We're not going to deal with the equation, but that's what it is. So what if I wanted to graph g of x, which is based on f of x, but a few different transformations? My recommendation is this. Whenever you deal with a transformation, always try to translate what it means to yourself before you actually try to graph it. So for example, I have a -1 in the middle. I take a look at my notes and I see that means move right 1. Then I have a +2 on the outside of the function, and I know that means move up 2. So let's go ahead and do this. So I'm going to take these 3 dots right here that I marked, and I'm just going to move them right one at a time. 1, 2, 3. Now I moved all these right. Now I'm going to move them up 2. 1, 2, 3. Once I have my 3 dots moved completely, transformed completely, now I can actually connect the dots right here. But notice I didn't move the whole graph originally. I just chose a select few dots. Usually only 3 are necessary. If it's a complicated function, you might need more. But I think that if you just use this technique for any sort of translation, any sort of like moving things around, it should be pretty easy. You have to do any crazy calculations, and then you can draw the graph afterwards. Because if you move 3 points, the rest of the graph will follow. So that's not too bad. But I think people have a lot more trouble with something that might look, well, like what we're going to do in a moment. So here's another example. Here's f of x, a nice absolute value function. But what I'm going to do is I'm going to transform it once again into g of x, which means f of 1.5x. So the first step is always, let's take a look at this half of x, and what does that mean? Isn't a half like, okay, isn't that compressing and stretching? And when you have a half, isn't it going to be compressed by a half? But wait a second. Do you guys remember what I said about being inside the parentheses, inside the function? It does the exact opposite of what we expect. What we think it means is times a half. That's going to flip things around. But instead of times a half, it's going to be times 2 over 1, or just times 2. So now with that information, we know it's going to stretch by 2. It's going to make it twice as wide. Remember, inside is horizontal, outside is vertical. So it's going to be stretching by 2 horizontally. Let's get 3 points. I'm going to pick these 3 points. Doesn't matter really what points you pick, but I'll choose those 3. Now, what I like to do here, guys, when we talk about stretching and compressing, it's a lot easier just to actually take a look at what these points are. So this is 2, 2, negative 2, 2, and 0, 0. And what's going to happen is, because I'm multiplying by 2 over 1, or just 2, by stretching it, I'm going to just take these points and multiply by 2. But does that mean I'm going to multiply every single number here by 2? Remember, horizontal is left and right. So think about it for a moment. What controls left and right? Is that the x values or is that the y values? Here's a hint. What's the 1/2 really close to? Oh, it's really close to the x. We're going to be multiplying all the x values by 2. So I could take the first point, multiply the negative 2 by 2, and I'll get negative 4, 2. That's a new point. I could take 0, 0, multiply the first 0 by 2, and that's still 0, 0 because 2 times 0 is 0. And then I would take the last point, 2, 2. I'm going to multiply only the first 2 by 2, and I'll get 4, 2. If I graph these new points right here, 1, 2, and 4, 2, and then I connect them, take a look at our new graph. Doesn't it look like it's like twice as wide? That's because we know we did it right. So if you ever wonder, how do I know if my answer is correct or not? Well, the easiest way to tell if your answer is correct is just simply check it visually. Does it look like we did the proper transformation? I know you guys might be feel a little iffy about this, so let's do one more example. So for this last example, let's go ahead and use the exact same function as last time. It's an absolute value. But let's make it so g of x is negative f of x. And if you're confused as to what that means, let it be negative 1 times f of x. So when we do this, remember the 1 doesn't really change anything. If it's bigger than 1, it makes it narrower. It makes it stretch upwards. And if it is less than 1, it's going to flatten it. but the negative is what flips it over. So which way is it going to flip? Is it going to flip left and right or up and down? If you remember, it's on the outside, so it's going to flip upside down, reflecting over the x-axis. So it kind of like uses x-axis as a reflection for the mirror. So remember what we did last time when we talked about multiplying with compression and stretching? Let's do the exact same thing. Let's get our 3 points. Let's do the exact same 3 points. And we're going to multiply those points by -1. But the question is, do we multiply the whole thing by -1, just the x's, just the y's? Well, think about it this way, guys. If we're flipping upside down, up and down, up and down, up and down, isn't that the y values? It is. So I'm going to multiply each y by -1. So I'm going to take -2, 2 and multiply the 2 by -1 to get -2, -2. 0, 0. Multiply the second 0 by -1 and just get 0, 0. And then we have 2, 2 and multiply the second 2 by -1 and it becomes 2, -2. Once we have our 3 points, I can graph them, connect the dots, make our shape, and voila! Doesn't that look like it's upside down? I think we did a pretty good job there, guys. So once again, visual reference. If we know it's supposed to be flipping upside down and it looks like it's upside down, that means we did a pretty good job. So if there's any questions that you have about this kind of stuff, guys, make sure you either ask in an email, come in during office hours, or, just save it for class. Otherwise, make sure you do this few assignments, a few problems, and you have a good day.